Welcome to Lecture 13, Abstract Syntax Tree, Chapter 9b, Syntax Analysis, Parser Design. Before we come into the detail for this lecture, let's look at the previous lecture's result. So far, we have been discussing the tokenization using regular expression. We have covered how to generate the abstract syntax tree using the parser and the context-free grammar, but we haven't touched the semantic analysis and the semantic graph and how to evaluate the abstract syntax tree. So that's the main focus of this part, this lecture. So what we will do is the following. We have the token that we created from the input. So the input has some file, and you create the tokens. And then after the tokens, we create a tree, syntax tree. Now, it's time to create the so-called semantic analysis and semantic graph. So it is a way to decorate the abstract syntax tree so that you can decorate that tree with a certain evaluation function so that you can evaluate this abstract syntax tree. And we call that decorated abstract syntax tree a semantic graph. So in this lecture, basically, we will talk about the decorated syntax tree as attribute grammar and how to evaluate the attribute grammars, and also the action routine. And we'll talk about the tree grammar and the syntax tree declaration, and to talk about how to generate the parser and using the recursive descent method to generate a parser. So let's get started with section 1, attribute grammars. So what is attribute grammar? Both the semantic analysis and the intermediate code generation can be described in terms of annotation and declaration of parsing tree. So what this really means is you have a parsing tree. You have something like this. You have time 2 plus 3 and 5. So that's a parsing tree we create. Then the value of this node will be 3. The value of this node will be 5. The value of this node actually is the value, so this nodes A, B, C, D, and E. So value of the B node will be the value of the C node plus the value of the D node. And this equation, we call it the action that you would take on the B node. So creating such a scenes and decorated on the tree, we call it attribute grammar. So attribute grammar basically is adding the function or evaluation methods to your abstract syntax tree. And that's what we want to do right now. So it actually is a kind of annotation, or you talk about it as, excuse me, or you talk about it as declaration of a parse tree or syntax tree. Attribute grammar provides a formal framework for decorating such a tree. So this actually is a formal way of doing it. The notes below discuss attribute grammar and their ad hoc cousin, action routine. So action routine is actually a cousin of the attribute grammar. And action routine, we do know about it. Say we have the expression, okay, defined as, assigned as expression plus expression, right? So this one we saw it before. And then this one actually is the so-called context-free grammar. And we would have the function associated with it that we call it action routine. So action routine actually is some function that actually is the implementation of attribute grammar. So these terms are similar, but grammar means it's written in some sort of mathematical form or formal framework. that we formally using mathematical to model it. Action routine is a function, it's a computer science term that use function to implement your HMB grammar. So here it's actually between the grammar and the function. HMB grammar is mathematical modeling. It is grammar. Action routine is implementation. It is functions. So we will start declaration of parse tree, then consider syntax tree. Consider the following LR grammar for arithmetic expression made of constants with precedence and associativity. So let's look at this thing. So HMB grammar serves to define the semantic of input program. HMB rules are the best sort of definition, not assignment. They are not necessarily meant to be evaluated at a particular time or in a particular order. So basically it's a grammar. So it actually is functional programming. It is by calling of certain function or tree recursive structure. So there is no specific or particular way or order to evaluate these different functions. So there's a left-hand side and right-hand side, and you use the function code to call it. So this one is the grammar we talk about. We have expression is okay, can produce expression plus term. Expression can be expression minus term. Expression itself can be a term. Term itself can be term times factor, and term can be term divided by factor. Term itself can be a factor. Factor can be a minus factor. Factor can be a parenthesis with expression. Factor can be constant. These are the calculators languages main content-free grammar that we noted. And this one, we can use it to build a syntax tree that we already covered it. So that is used for the content-free grammar to create the abstract syntax tree. Now let's look at the declaration portion. So that is a set of the grammar that we have. So the grammar will generate properly formed constant expression over the basic arithmetic operator. It says nothing about their meaning. To tie this expression to mathematical concept, we need additional annotation. So the most common is based on attributes. So attribute is what? Data field, function, value, okay? Attribute is the attribute that we use in computer science. It's some sort of data field, right? You have an object has some attribute, and the attribute actually is either a function or it is actually a data field that we talk about in object-oriented programming. It's member field or attribute. Attribute can be function. In our expression grammar, we associate a value attribute to these different grammar two rules. So you actually will have value or function. So the symbol S, starting symbol have a starting symbol's value will be the meaning of the attribute value, and the token string from S. What that means? Your S is your topmost node, your S node. Okay, so S has a value, and this S value actually is times, right? And then actually 2, okay, and then plus, and then 3 and 5. Okay, so here you have the value of this one, CW and DW, and here you have BW, something like that. Okay, so these are some attribute a certain node, the node of your tree. Okay, so here we have the bottom-up content-free grammar for constant expression. So we are assuming that the value of a constant is provided by the scanner. So the value of the factor is very easy. Okay, so these so-called content-free grammar can have a declaration, or we call it attribute grammar as the following. It's a grammar coming from content-free grammar, and content-free grammar decorated into attribute grammar, okay, with declaration. So let's look at 4.1. So in 4.1, you have E1 equals E2 plus T. Okay, we differentiate the E and T. Okay, E have different type of E. Okay, so with that, so with the grammar rule, we have these E1, E2, and E. Okay, T1, T2, and T, F1, F2, and F. Okay, so these are the basic function. So we create the so-called attribute grammar on the right. So E1 value is the sum of E2's value and T's value. Okay, so here you have a content-free grammar on the left. Okay, and the evaluation of each node actually is using this such a function. And we can use this to build our tree to decorate each node on the tree with these action functions. So we call that attribute grammar. So attribute grammar is content-free grammar with evaluation functions. Okay, so attribute grammar redux version. In the strict definition of attribute grammar, copy rule and the semantic function call are the only two kinds of permissible rules. Okay, but we actually can use what the so-called triangle, white triangle, to denote the so-called function call. So we can use that. Okay, we can use that. Okay, right here. This actually, let me see. It's a little bit bizarre. I see because of copy, this one may actually be out of place. Let me move them back. Okay. Okay, the first dual. This one actually. Okay, there are some symbols that we actually are missing. So let me put them in space, the right space. Okay, sorry for that. Let's continue. Sorry for that. Okay, so basically we can use that symbol to introduce each call fragment corresponding to a single rule. In practice, it is common to allow rule to consist of small fragment of code in a small, well-defined notation. Okay, so these semantic function can be written inline, so it will be put onto the tree. Okay, put onto the tree. So HMB Grammar Redux version, in Redux notation, the rule for the first production in figure 4.1, we can write it down in such a format. Okay, such a format. So here you have the list equal ID and the list tail, and this tail actually is comma and list. Okay, and this tail is empty string. So these are the rule that we written down for the comma separated list. Okay, so that you can use such notation for it. It is a Redux version compared to this version, but we just need some sort of notation for it. Okay, now the purpose of attribute grammar is to associate meaning with grammar. We can use any notation and type whose meaning are already defined. So basically, it is just the way you decorate it. Okay, and these are not function code; these are grammar. So you can write in the way that it makes sense. Okay, so in example 4.4, 4.5, we associate numerical values with the symbol in content-free grammar, and thus with the parse tree node using semantic function draw down from ordinary arithmetic. In the compiler or interpreter for full programming language, the attribute tree node might include the following. It will include the following: include a identifier or reference information about a symbol table. So that maybe is reference information about a symbol table. So that maybe is A actually equals B or C. Okay, so there's a reference. So basically you have a node. Okay, you have node, and that node may be A node, and A node actually pointing to a symbol table. Okay, and that also there's a reference, there's a type. Okay, and these are different things that you decorate onto the node. Okay, and from statement expression, a reference to corresponding code in the compiler's intermediate form. Okay, and for almost construct indicate of the file name line column. So each node also we associate with the file name node column, okay? And for internal node, okay, a list of semantic error, also error will be actually included. So basically, these are not just the mathematical calculation, but also we're including the so-called reference type and reference and different things that will decorate your tree. So this one, let me jump a little bit further away to the end of this portion. So you can see that each node may have the thing like error, simple table, link, and type. Okay, a lot of things associated with a decorated tree. But we are not here yet. Okay, so far we just look into the attribute grammar. But right here, this attribute grammar do talk about the possible nodes declaration or the attribute of the tree node might include this different thing. And this different thing, if you look at the result that we decorated, it is something like this, okay, something like this. But we will go into step to introduce how to decorate a tree, okay, how to decorate a tree. So section two, attribute grammar part 2, okay. So attribute grammar is a special form of the content-free grammar. It's a decorated content-free grammar where some additional information attribute will be appended. So you may have error, you may have line number, you may have simple table, you may have value, you may have another thing being associated with the node, okay, appended to the node and non-terminal node in order to provide context-sensitive information. Each attribute has well-defined domain of value. It may be integer, maybe float, maybe a function call, maybe some expression, okay, and may have line number. Attribute grammar is a medium to provide semantic to the content-free grammar. So content-free grammar only give you the so-called production rule, and it build a syntax tree by to evaluate your program. You need to have the attribute grammar and decorate it, and also it may report an error. Okay, it may also so attribute grammar is the data structure that we use to evaluate a program. Okay, so attribute grammar, okay, can pass value or information among the node of a tree. So here we do have actually produce E plus T, expression produce expression plus T, okay, and eta value equals eta value plus theta value. Okay, this is another way to write it. The right part of the content-free grammar contains the semantic rule. Okay, these are only the value part, and the non-terminal node may have more attributes. So let's continue. Semantic attributes may be assigned to their value. So that's a semantic attribute from their domain at the time of passing and evaluate at the time of assignment and conditions, based on the way the attribute get their value. So this, we actually divide the attribute into two types. So now because of the evaluation, we divide the attribute into two types. So each node will have some attribute, and the attribute may have two types. One is synthetic type, one is inherited type. Okay, let's look at what are these two types of attribute. So attribute grammar carries some semantic information along with the parse tree. Okay, so useful for static semantic speech supplication and semantic checking in compilers. So attribute grammar is a content-free grammar that we know with annotation, and annotation is an attribute, a set of attribute values. Okay, and the error and the line number, and they are different values. So actually, each node has extra data field. Okay, let's assume that each node is an object, and they have different value over there. Each production rule has a set of functions. Each production rule has a set of functions that define certain attribute of non-terminal in the rule. Each production rule has a set of predicates to check the attribute's consistency. Value derivation have predicates true for each node. Okay. So here we start to look at the two types of attribute. One type is synthetic attribute. Syntactic attribute are determined from the node of child in the parse tree. So that's what that actually is. Syntactic attributes example is that you have the plus sign, you have 2 and 3. So this node's value is depending on the sums. These are actually called syntactic attribute. So your value is actually generated by the sums. You synthesize it using your component to build your value. That's called synthesized attribute, okay, or S-type attribute, okay. There's another type called inherited attribute, okay. Inherited attribute are determined by parents, siblings, okay, in the parse tree. Pass the semantic, actually pass the information down the tree. So this one actually is what? You have, say you have x equals a plus b. So this one is an integer, this one is an integer, this one actually is an integer. So the type of the variable, that is one kind of attribute. So the type of the variable is an attribute. And that type of attribute actually is what? It is a inherited attribute. So inherited attribute means that your value of that attribute is determined by your brothers or your father. Your brothers or your father. Father means that you are upper node. Okay. Father means that this assignment statement may determine the type of this guy. Okay. And its value may also be determined by its sibling to determine it. So basically that is the attribute, this type of the attribute, the type is one example of the inherited attribute. So this is I-type attribute. So basically you have S-type attribute and I-type attribute, two types of attribute that we talk about when we talk about here. The attribute have two different types. Okay, attribute have two different categories. One is synthesized attribute, one is inherited attribute. Okay, and those attributes are here. The synthesized attribute, that the value determined by the sums, and the value determined by the parents is called inherited attribute, parent and siblings. Okay, so synthesized attribute is that your S rule produce ABC, and ABC's rule in value in combined would be the value of the S, and we call S is synthesized attribute. S, that attribute is a synthesized attribute. So S take the value from the child node ABC. It is said that a synthesized attribute of the node S is actually synthesized from the value of ABC. Okay, so expression produce E plus T. The value is a synthesized attribute. The type is a inherited attribute. So in contrast, the synthesized attribute, inherited attribute can take form from parent or sibling. So A can take value from S or B or C. B can take the value from S or A or B. Likewise, C can take value from A, from S or A or B. So this one actually is the synthesized attribute, and type of a variable actually is a inherited attribute that we explained it already. So right here, expansion, when a non-terminal is expanded to terminal as per grammatical rule. So here you can expand your syntax tree or evaluate and go up. That's called reduction. So reduction and expansion are two different directions for tree. Reduction. So reduction actually you kind of evaluate from bottom up and reduce the value and get the value for the top level. So when the terminal is reduced to the corresponding non-terminal, according to a grammar rule, we call it reduction. Syntax tree are parsed top down and left to right. Okay, where does reduction occur? We apply its corresponding semantic rule to it. Semantic analysis use semantic directed translation to perform the above task. Semantic analyzer receive AST, the tree, from the previous stage, the syntax analysis. Then we need to decorate it. So semantic analyzer attach the attribute to AST. So here, this one is semantic analyzer. Semantic analyzer is based on your context-free grammar to add the decorated annotation to the tree. So it is also part of the parser. So first part of the parser is based on your context-free grammar to generate a tree. Second part of the parser is using the tree or the or with the syntax with the attribute grammar, and then to generate the so-called attributed tree or decorated tree or attribute grammar or attribute semantic graph. Okay, so attribute are two tuples. So there is attribute name and attribute value. So for example, can be type integer and the present value 5. So integer 5 value equal 5. There are two attributes associated with the node. That is type integer and the present value 5. Okay, for the value node. So here we have syntax directed translation scheme. So we have 2 times 6 plus 4n. So here we actually have the value of each node. Okay, value is a node. So basically 2 is a digital, it's actually a number. Number is a factor, factor is a term. And then 6 is also a value, that's also a factor. Okay, so turn actually times factor become a term. Okay, and here 4 is actually a value. So 4 is a value, is a factor, and it actually is a term. And then turn plus turn. So here we have actually expression plus term become an expression. So 2 times 6 actually plus 4 n. Okay, and here you have the n. So that actually n is over there. So this one, okay, this one I think n is the end of the line. Okay, n is not really the number n. Okay, so there's no time. So this one is the tree. Okay, so syntax directed definition. So this is syntax directed translation. The concept view of the syntax directed translation, input stream, path tree, and dependence graph, and evaluate order of syntax semantic rule. So this is so-called syntax directed translation. Translation means you do evaluation. Okay. And there's another type of syntax directed definition. So it's a generalization of context-free grammar in which grammar symbol has associated with attribute with rule. So each symbol associated with attribute and rules. And attribute are associated with grammar symbol, and the rule are associated with productions. So S attributed SDT, okay. S attributed SDT. SDT is the syntax direct translation. So if a SDT use only synthesized attribute, we call it synthesized SDT. So SDT, you can think about it as its evaluation flow. Okay, so here you have S-type SDT. So you have E value equals E value plus T value. That is S attributed SDT. Okay. So as depicted above, the attribute in attribute SDT are evaluated in button-up format, okay, that we know. So there's another kind called L attribute. So this formula SDT used both synthesized and also the inherited, okay. So L attribute, so S is sum, right? S is sum. L is actually from top or the sibling, okay. So that's actually L from top and sibling. So that L type SDT, okay, it's actually used, may use a synthesized or inherited attribute. So S attributed SDT is also part of the L attributed SDT. Okay, so L attribute ADT, a non-terminal can get value from its parents, child, sibling nodes as the following. Okay, so S can take value from A, B, C, and A can take value from S only, and B can take value from S and A, and C can take value from S, A, B, okay, whatever. So S attributed SDT is part of the L attributed SDT. Okay, because L attribute SDT can evaluate the synthesized attribute as well. Okay, so it's something like this. So attribute in L attributed SDT are evaluated in depth first, left to right grammar. So it actually is similar to recursive descent. Okay, we may conclude that a definition of S attribute, definition is S attributed, then it is also L attributed as L attribute definition enclosed S attributed definition. Okay, that's the relationship of this syntax directed translation. That actually is the so-called evaluation flow based on the syntax. Okay, now we go into the next section, that's evaluating attributes. So we have this different type of attribute, and we know that how we can actually perform the syntax directed translation. So this is a very simple attribute grammar. Each symbol may have at most one attribute, and punctuation mark have no attribute. So this attribute is so-called synthesized attribute. Okay, the very simple way is you only have one as a attribute. They are evaluated from the attribute since below. This actually is for certain arithmetics. Okay, in general, we are allowed to use a synthesized or the inherited attribute. But if you look at it as using the simple version for arithmetic, you do not have the inherited attribute. Okay, so inherited attribute may depend on things above or side of them in the past tree. Okay, inherited attribute of the start symbol can constitute runtime parameter of the compiler. So some value actually coming from compiler, you can actually using the L type to transcend to the whole tree. Okay, to transcend to the whole tree. That's called L attribute, and it's a parameter for compiler. Okay. So evaluate attribute. The process of evaluate attribute is called annotation or declaration of the path tree. Okay, when the path tree under this grammar is fully decorated, the value of expression will be the value attribute of the root. Your end result will be that. Okay, the code fragment of the duo can call semantic function. So to get the value, we call it semantic function. So semantic function is a way to evaluate your attribute. Okay, that has another name called semantic function. So here we have 1 plus 3 parentheses times 2. You come from constant 1 is a factor, it's a term, it's an expression. Constant 3 is a factor, it's a term. Expression plus term is an expression. So we get a value of 4. And then expression with the parentheses outside that actually become a factor. Factor is a term, okay? And 2 is a constant, is a factor, and term times factor is a term, and term is an expression. So by doing this, we actually build up the syntax tree. And when we evaluate 1 plus 2 F plus 2 T plus 2 E, and E plus 3 plus 2 F plus 2 D, T E plus T, you pass to E, parenthesis E, you actually pass to E, E plus 2 T, 2 plus 2 F, 4 times 2 plus 2 T, T plus 2 E, and thumbnail have the result for the evaluation result. So top-down content-free grammar and the pass tree for subtraction. So here we have 9 minus 4 minus 3. This one is actually top-down content-free grammar, but as you can see, it is top-down, but it actually the grammar is built up in the LR format, okay, in the LR format. So here you have such evaluation tree, and you can decorate it. You can decorate it. We will decorate it, okay. We will decorate it to get such a result, okay. But before we do that, let's actually look at these different rules. So this syntax tree is like this, okay. This new syntax tree is like this. Top-down confidence free grammar and the pass tree for subtraction. If we want to create attribute grammar that accumulate the value of overall expression to the root, we may have a problem because subtraction is left associative, but this one apparently is right associative. So this one is not okay if we use this grammar, okay, if we use this grammar. And this one is LL1 grammar, but LL1 grammar that is, it won't work, okay, it won't work. So here, actually, if we use that, if you want to decorate the button up as attribute, okay, we cannot do that, okay, because your right subtree doesn't have a value, okay. We must prepare to describe arbitrary number of the right operand, okay, in the expression tail, okay. This actually indeed possible, but it defeats the purpose of formalism. In fact, it required us to embed the entire tree to the attribute of a single node. That doesn't make sense, okay. So LL1 grammar does not fit the S attribute grammar, okay. This one is a rule. You don't do that. Decorate tree with left to right attribute is called L attribute. If, however, we allow passing attribute value not only left to right attribute, but also left to right attribute from also left to right in the tree, then we can pass 9 to the topmost expression node where it can be combined. So if you only use the S attribute, you cannot evaluate it. But now you can pass the 9 to here, and it will work, okay? If it's L attribute, you can pass from your sibling to it, okay? If you use the S attribute, you just evaluate from bottom up, this one won't work. But L attribute in here, it will work, okay? L attribute, it will work. So S attribute doesn't work in this case, LL1 grammar, but L attribute actually works. So basically, you start to decorate it. Here, you actually get the constant and the 9 being passed to the sibling. And sibling minus 4, you get 5, you pass to the sibling. 5, actually, this, you pass the value, and eventually you pass it back, okay? So that actually is the value, okay, the value and the state variable, ST. It actually is from your sibling's value, okay, your sibling's value. From the left, you pass over. You take the value from your big brother, okay, the ST previous result, okay. So this one, ST is a L attribute. So using the L attribute, you can pass the value to it, but value is a S attribute. So with the help of a L attribute, you kind of being able to evaluate this passing tree, okay. So top-down attribute grammar for subtraction. To effect this style of decoration, we need the following attribute. So basically, you need to allow the L attribute. To allow the L attribute is that your tails ST, your constant, your tail ST will actually get from constant val, okay? So you constant pass to its sibling, constant pass to sibling, but the father actually get value from the tails value, okay? So this is the so-called value. ST is the value, is actually previous value, and is actually called subtotal. So subtotal of the previous term can be passed to the sibling. Subtotal of the previous result, subtotal of the previous result, subtotal of the previous result, okay? ST is subtotal. So use ST actually is the so-called ST actually the so-called L attribute, okay? ST is L attribute, and we decorate the country. So here show you that, okay, your content-free grammar can be decorated in different format, S attribute, or you can decorate in L attribute for the same syntax tree, okay? And that depends on how you write the attribute grammar, okay? So here we rewrite the attribute grammar for all of the terms like this, okay? And top-down attribute grammar for constant expression. We can flesh out the grammar fragment to produce a more complete expression, okay, as shown in 4.3. So this one is a more complete attribute grammar, okay? And the underlying CFG for the grammar accept the same language in 4.1. So actually it's the same as what we see in 4.1, figure 4.1. Figure 4.1 is here, this one. This one actually attribute grammar. You can also use the one we have to decorate it. Okay, to decorate it. That's a 4.1. So, but where we allow SLR, this one is LL1. Okay, attribute flow for the parts of the 1 plus 2 times 3 using LL1 grammar. That one is shown in here. So in here we also have 1 plus 3 times 2. So this one say that we have 1 as a constant, okay, is a factor. And then here epsilon n of 3, so the value being put over here that actually is subtotal. Subtotal is passed back to here. And then this is a term actually term plus term. And here we have plus 3 is a constant. So basically the subtotal will pass to here. So you see that this one actually is a little bit more complicated compared with the S attribute only. Okay, the S attribute only evaluation is here. But with L attribute, it's kind of more complicated. Okay, kind of more complicated. So that actually is the so-called LL1 grammar, okay, using the LL1 grammar. But LL1 grammar apparently is not very efficient, okay? So here you have a subtotal. Okay, that's the new grammar. So evaluation attribute, this attribute grammar is good, a good bit messier, okay, than the first one. But it is still L attributed, which means that the attribute can be evaluated in single left to right pass using the input, okay? In fact, this can be evaluated during the LL parsing, and each synthetic attribute of left-hand side symbol depends only on the right-hand side symbol, okay? Okay, each inherited attribute of right-hand side symbol depends on the inherited value of left-hand side symbol and the synthetic side of the attribute of the previous one, okay, previous one to the left. L attributed grammar are the most general class of attribute grammar that can be evaluated in LL space. So LL passing like to use a L attribute grammar, okay. So these are certain tasks, such as generation of code for short circuit Boolean expression evaluation that are easier to express in non-L attribute. Okay, so short circuit do not like the L attribute, okay, because the potential cost of complex traversal scheme. However, most real-world compiler insist that grammar to be L attributed. So some compiler really want L attributed, okay? So far, we actually look into the so-called attribute grammar, and they are more mathematical. So from the next section, we are going into the function that is the attribute flow and attribute functions. Now, assuming that the attributes are well decorated onto your abstract syntax tree, and we will have some tree and with the production action. So we have that. So this, we start to evaluate the attribute. So we will need to have attribute flow, and attribute flow algorithm propagates through the attribute value through the path tree by traversing through the tree. So you go down to a tree step by step, okay, based on certain rule. So the design of evaluating the attributes, including the production rule, and you use the production rule to generate the so-called attribute grammar, and you come up with a production rule, and you also knowing that each node should have the S attribute that get the sum from the lower portion, or it get the inherited value from its left side brother, okay, the L attribute grammar. And then there's an algorithm called attribute algorithm. So these three are necessary. Okay, these three are important to evaluate the attribute. We call this one is the attribute flow algorithm, including the production rule, action, and also attribute flow. So here we have a E will be producing T and T tail, 10 and 10 tail, and then the 10 tails subtotal would be assigned by the value of the T. So T passes to it. This one is an L-shaped value. Okay, L-shaped value pass to there. The subtotal get from the previous one. Okay, so T2's subtotal would be getting from T1's subtotal plus the T's value. Okay, so this one we actually have different rule and it's related calculation for the action plan and the attribute grammar. So attribute flow, both context-free grammar and attribute grammar do not specify the order in which the attribute rule should be invoked. By notations are, both notations are declarative. They define a set of value tree, but they don't say how to build or decorate it, and therefore, the evaluation flow and the attribute flow, okay, they really depend on your way of doing the grammar, how you do graded recursive descent, or you actually performing the so-called LR grammar. So actually, it really depends on how you build a tree and evaluate the tree. The order in which the attribute rules are listed for a given production is immaterial. Attribute flow may require them to execute in any order. If in figures 4.3, we were to reverse the order in which the rules appear in production rule 1, 2, 3, 5, 6, and 7, it would be purely cosmetic change. The grammar will not be altered. So grammar may not be changed, but you can run in different way. So attribute flow, and attribute flow by itself is an algorithm that decorates path tree by invoking the rule of an attribute grammar in an order consistent with the tree's attribute flow called translation scheme. So we do talk about the translation scheme before. It actually is the so-called syntax translation, okay, the syntax translation plan that we talked about it before. And that is the L attributed or S attributed. That is related to your attribute flow. The simplest scheme is the one that makes repeat process over the tree, invoking any semantic function whose argument have all been defined, and by stopping when it completes a path in which value has no change. Okay, you can actually kind of shaking it and then until it's settled. Okay, that's how it is. Such a scheme is said to be oblivious. Okay, actually, it's wasting time. Actually, in the sense that it exploits no spatial knowledge or of either the path tree or the grammar. It will hold only if the grammar is well defined. Better performance, at least for a non-circular grammar, may be achieved by dynamic scheme that tailors the evaluation order. So if you tailor the evaluation order to the structure of a given path tree, for example, by constructing topological sorting of the attribute flow graph, and then invoke the rules in an order consistent with the sort, then it may speed up. So there are several kinds of compiler: one-pass compiler, multiple pass compiler, low and go compiler, and upper nine compiler. There are so many different compilers. Okay, so actually, so your evaluation tree may go one pass, two pass, many pass. Okay, so one-pass compiler, a compiler that interleaves semantic analysis and code generation with parsing, is said to be one-pass compiler. Okay, so you actually mix up the so-called tree generation and also the semantic analysis for declaration. We call it one-pass compiler. And it is unclear whether interleaving semantic analysis with the parsing make a compiler simpler or more complicated. It's mainly a matter of taste. Okay, but usually one-pass compiler is right now is only used for very simple language. Okay, it actually is not really that efficient. If intermediate code generation is interleaved with parsing, one need not build a syntax tree at all. Okay, you don't need to build a syntax tree. You can directly do evaluation. So those are some type of the simple language, such as calculator language. You do not need to build a syntax tree. You use a regular expression and you evaluate through the rules and you can get a result. Okay, moreover, it is often possible to write intermediate code to a output file on the fly, rather than accumulating it in the attribute of the root of the parse tree. The resulting space saving were important for previous generation of compiler, which had very small memory. On the other hand, semantic analysis is easy to perform during a separate traversal of syntax. So basically, you use a separate different paths, 2 paths or 3 paths. It is easier for the semantic analysis. So one path may not actually buy too much in semantic analysis, because that tree reflect the program semantic structure better than the parse tree code. Parse tree does, okay? And especially when top-down parser, because one has the option of traversing the tree in an order other than the chosen by the parser. Okay, bottom up and top down HMB grammar to build a syntax tree. If we choose not to interleave parsing and semantic analysis, that is multiple paths, we still need to add attribute rule to the content-free grammar. So this is still needed. So with the attribute tree, you can deal with the so-called function call and also the stack. Okay, but they serve only to create syntax tree, not to enforce semantic rule or generate code. So figure 4.5 and 4.6, 4.5 and 4.6, 4.5 and 4.6. These two are actually one button up, one top down, two way to construct the syntax tree. And they are top-down grammar with respect to build syntax tree. Okay, the attribute of in this grammar holds neither numerical value nor target code fragments. Instead, they point to a node of the syntax tree. Function make leave return a pointer to a newly allocated syntax tree node containing the value of a constant. Function make an operator, unitary operator, and make binary operator return pointer to a newly allocated syntax tree node containing unitary or binary operator. Okay, so figures 4.7 and 4.5 showing you the parse tree for this simple expression using the grammar in 4.5 and 4.6. So 4.5 is actually bottom up. You evaluate everything from bottom up. Okay, it's 4.6 actually is top down. So you pass the value from previous node to, so you use the subtotal. So with that, your 4.6 is bottom up. So you decorate your tree, and then 1, 2, 3. Okay, so you actually decorate your tree, and then it's Q. Your partial result is actually gradient descent. Okay, so This is button up. You button up, you build up your button up tree. Okay, and it actually evaluate like this. And this one is a top down and use L shape. Using a subtotal from previous node. Okay, so it's two different syntax tree. Action routine, they are automatic tool that will construct a semantic analyzer, attribute evaluation, okay, evaluator for given attribute grammar. Application, attribute evaluator generator have been used in syntax-based editor, incremental compiler, okay. Most production compilers, however, use an ad hoc handwritten translation scheme, interleaving parsing with at least the initial construction of the syntax tree and the possible or semantic analysis of under the intermediate code generation, because they are able to evaluate the attribute of each production as it is parsed. They do not need to build the full parse tree. So this one, usually ad hoc compiler, you do not need to have a full parse tree. So they will get some partial result and then use it. So that will save space. So action routine function. So action routine is a semantic function that a programmer instructs the compiler to execute a particular point in the parsing. Most parser generates allow the programmer to speech by action routine. In the LL parser generator, an action routine can appear anywhere within the right-hand side. So the function can always show up in the right-hand side, and you can evaluate and create a value for the right-hand side. A routine at the beginning of the right-hand side will be called as soon as the parser predicts a production. A routine embedded in the middle of the right-hand side will be called as soon as the parser has matched the symbol to the left. So left side match, you continue. Left side match, you continue. Okay, the implementation mechanism is simple. When it predicts a production, the parser pushes all the right-hand side onto the stack, including the terminal and the pointer to the action routine. When it finds a pointer to an action routine at the top of the parse stack, the parser simply calls it and pass in the appropriate attribute as argument. So basically, you evaluate a function. And then top-down action routine to build a syntax tree. So here we have a top-down syntax, okay? And you use the subtotal. So it actually is L-shaped grammar, okay? It's LL1 grammar and L-shaped attribute. And you can use the recursive descent and action routine on it, okay, using this one. So that the grammar, and then you change your recursive descent passing based on it, okay? So here tell you that actually L-shaped grammar, the recursive descent evaluator. Pattern evaluation, LR parsing generator cannot, in general, embedded action routine in arbitrary place on the right-hand side because you don't know when it will be called. So basically, it tend to use the S-shaped attribute, okay? So if an attribute flow of the action routine is strictly buttoned up, okay, then the execution at the end of the right-hand side is all that needed. The attribute grammar, okay, grammar are essentially identical to the action routine version. If the action routine are responsible for a significant part of the semantic analysis, however, then they will need contextual information in order to do the job. To obtain and use this information in an LR process. So basically, this one just tell you that, okay, LR parsing need a S attribute grammar, and then it need to build the things from bottom up, and you cannot show up the action routine. You cannot bind the action routine, action function, the routine function, okay, action routine function. You cannot bind the action routine function at any location that you like, okay? So the space management of the attribute, any attribute evaluation method requires space to hold the attribute of grammar symbol, okay? The detail differ in bottom-up and top-down. The bottom-up parser with S attribute grammar, the obvious approach is to maintain a attribute stack. So you like to have a stack is pattern up and directly mirror the passing stack. Okay, so there's a passing stack, and you actually have the attribute stack. So two are actually combined. So stack approach is more appropriate for this button up things. And next to stay number on the pass stack is a attribute record for the symbol that we shift when we enter that state. Entries in the attribute stack are pushed and popped automatically by the parser driver. Space management is not an issue for the writer of HMB. Okay, so this one just talk about management. For top-down parser with L-shaped, L-attribute grammar, we have two principal options. The one option is automatic, but more complex than button-up grammar. So usually L-shaped is more complicated. It is still using attribute stack, but one does not mirror to the pass stack. The second option has lowest space overhead. So this one has less overhead space, but save time by shortcutting copy rules. The best thing is the gradient descent backtracking is actually wasting resource. Okay, anyway, these are the execution of the attribute flow. Next one is the syntax tree declaration, part 1. Okay, so figure 4.11 contain a button-up configuration, CFG, okay, content-free grammar for a calculated language. Okay, so the diagram differ from the example 2.37 in three ways. One, we allow the declaration to be intermixed with statement. Two, we differentiate between integer and real constant. Three, we require explicit conversion between integer and real operand. The intended semantics of our language require every identifier be declared before it is used. So this is 4.11, and it's content-free grammar for calculator with type and declaration. So even some of the value are real, some of them are actually integers. Okay, so you can compare this one with the previous version. So it's extrapolating from example in figure 4.5. It is easy to add semantic function and HMB routine to the grammar of 4.11 to construct a syntax tree for the calculator language. The obvious structure for such a tree would represent expression as we did in 4.7, and would represent a program as linked list of declaration and statements. A concrete example 4.12 contains the syntax tree for a simple program for the average of the integer and real numbers. So this one we have integer A, get the A from outside, and then real B and real B. Okay, and then you actually calculate the sum. So basically, program is we have the integer declaration, and then followed by read A, and then real declaration, and followed by read B, and then we will write the following thing: the evaluation of this one, the division, okay, plus and flow, okay, button up syntax tree. So this example use the example, okay, to conclude our discussion. Okay, basically this finish the chapter 1 to 4. That these chapters are the number for the programming language programmatic book. Okay, so something like that. Here we actually finish the discussion of the lexical analyzer and the parser. Okay, so basically that is a language that we use. Okay, so here we have the integer and also have the real number now. Okay, this one is a production rule. Okay, for the 4.12. Okay, and then the tree grammar for the calculator. Okay, so the notion A column B on the right hand side is a production rule, means that A is one variant of B and may appear anywhere B is expected on the right hand side. Okay, let's go back. So here is a column. So this one is the production load. So integer declaration means that item, okay, item, an item can be integer and item, okay. I'm sorry, identifier and an item, okay. So here, that's the definition of the new set of grammar. And tree grammar and content-free grammar differ in different ways. A content-free grammar means to generate a language composed of a string of tokens, where each string is the year of a parse tree. Parsing is the process of finding a tree that has a given year. A tree grammar, as we use it here, it is meant to generate a tree themselves, okay? So the grammar for calculator language is type. So now we have type. So type is also some attribute we need to deal with. So right here, each node of the tree, including the following attribute, inherited attributes such as error and simple table location, okay? And synthesize attribute that get from that will be your location, your error, and your type, and your name, okay? It's IP only. So these are different attributes for each node now, including the inherited, okay, and the synthesized different attribute. Okay, so there's a simple table, and we actually will put some information into the simple table. And our handling of semantic error is propagation. We make the error in the attribute. So attribute will propagate according to the rule, of the evaluation. So right here, we have classes of node for syntax tree attribute grammar. So here we have a program have no variant, okay, and then program inherit no feature, okay, and this item can be, these are items, okay, these are variants of items, okay, and expression, these are variants of expressions, okay. We have different attribute for these different ones. So here slightly we modify the syntax of the content-free grammar, okay, and attribute to actually create these different variants, okay, and then you design the your grammar with the declaration, okay. So here we actually design it in this way, okay, in this way, and then evaluation functions, and then after we declare that tree, okay, and the content-free grammar, these are the one for the calculator project, okay, calculator project. So it has the decorated AG, okay, attribute grammar that actually is in 4.15. Let me see, 4.15, 4.15 is this one. This one is the final declaration of the grammar. So for each node and how each attribute pass through, that is one part of it. The other one is content-free grammar. Content-free grammar is the grammar we actually shown here based on those attributes, okay? So tree and attribute, this is content-free grammar, they are combination, and syntax tree of the 4.12. So that means the language actually will be used to generate such tree, and the tree will be decorated with the function that we mentioned in 4.14, and then at the end you will build a declaration of syntax tree in this way, and it is runnable, and it is following what we talk about today, the action routine, and also following what we talk about today, the so-called attribute flow, okay, evaluate through the tree to get the different attribute. And that's the purpose of today's talk, the evaluating of the attributes. Section 8, building recursive descent parser. We have already finished the theoretical part for the parsers. Now let's look at how to build a recursive descent parser. So we need to check the type, number, and digit, and actually perform the evaluation as well. So building a recursive descent parser. Parser are programs that help to process text. Compiler and the interpreter use parser to analyze programs before processing them further. And the parser for formats like JSON, YAML process text into programming languages' native data structures. In this article, we are going to look at how to build recursive descent parsers. Recursive descent parsers are a simple but powerful way of building parsers. For each entity in the text that you want to process, you define a function. So basically, you keep defining a function. This one, we already talked about it in the previous lecture, that you use the recursive descent way to evaluate your function. So that one, we actually can go back to the previous lecture to look at it. Okay, you can evaluate each actually try to match each function and evaluate it over there. So, okay, so basically, let's see. Okay, so first, we are going to look into some of the theory underlying parsing. Okay, so here the theory will be lighter than previous one. We are talking about the implementation theory here. Then we will use Python. We are going to build a calculator and a JSON parser that supports comments, trading commas, and quoted strings. Finally, we are going to discuss how you can build parsers for other kinds of languages that behave differently than the aforementioned examples. If you are already familiar with the theory, you can directly skip to the part where we build the parser. So let's look at the basic theory. How does parsing work? In order to process a piece of information, a program performs 3 tasks. That's called lexing or tokenization. That's step 1. We talked about it already. The program goes over the character in the text and extract logical group called tokens. For example, in an expression such as 3 plus 5 minus 10, a program to process arithmetic expression can extract the following tokens. So basically, you have 3, that's a token, plus is a token, 5 is a token, minus is a token, 10 is a token. So this portion, we talk about it in lecture 10 and 11 about how to do tokenization and determine the type of the tokens and also the value of the tokens. So how does parsing work? Okay, then we go to the step 2. The program then uses Duo to identify meaningful sequence of a token, and this is called parsing. The Duo used to make this happen is called grammars. The previous tokenization, we only talk about the symbol and validation of symbol or words. Now, grammar means that the structure between the words. So much in the same way that words of the natural language like English are strung together into a meaningful sequence using English grammar. Individual rules of a grammar are called productions. Production means you have the non-terminated term such as E produce, E times E, that actually is a production rule. Okay, so here we talk about the structure of the terms, structure of the words. Okay, how does parsing work? So basically, imagine that we build a program that processes a mathematical expression, and we are interested in addition and subtraction. An expression must have a number such as 3, and then followed by a number operator such as plus. Okay, and then actually the duo can be like this. So basically, you have one number followed by a operator and number and 0 or more. Okay, so this is the duo for your expression. So you can have number, and by itself, it's actually is a expression such as 3 is an expression, or 3 plus 5 is an expression. 3 plus 5 plus 2, that actually is another expression. Okay, so here we have these. Okay, How does parsing work? Finally, the program takes a set of action for the grammar rule. Okay, this is the action routine that we talk about in this lecture. For example, after parsing, our math program would need to calculate the value of the expression. So those are action functions or action routines that we take to evaluate each one of them. So you make your rule, and then we, based on the rule, call in a rule to do it. Okay, so this one, let's look at it, the relationship. So we have a expression that is expression times expression, okay? And your expression can be a term plus expression, okay? So here, let's see, that's actually this one I made a mistake. This one actually is a operator, okay? This one can be an operator. So this one actually should be an operator, okay? Okay, so these are actually the so-called expression, and we talk about the declaration. So basically, the value of the expression on the left-hand side will be equal to the value of the expression one doing operation with the value of expression two. Okay, so here expression one, expression two, this one expression on the left-hand side. Okay, so this one we have the action function. Okay, so basically in your parsing, you do have a parsing tree, right? And each expression or each production rule actually is this structure here. Okay, you have this structure here. So you do parsing maybe from bottom up using S attribute, or you actually go through passing the subtotal to the neighbor siblings. So you can do express the evaluation. These we talk about it many times in the current lecture. So basically that is a evaluation flow. We call it the attribute flow, right? Attribute flow. So we use the attribute flow to actually evaluate the action routine. And then we may go button up to evaluate, we may go passing the data to the sibling, two possible ways, S attribute or L attribute to evaluate. But eventually the whole thing will be evaluated for the program, okay, for the program. So that is our evaluation tree. So we talked about it already, but here the key point is they are function calling function and they do it recursively. So we need to apply the recursive call of the parser and the evaluator over your syntax tree. That's what we learned. So in our chapter, lecture 8, in our lecture 8, we talk about tree. And we talk about the evaluation of the tree. We talk about the evaluation of tree, okay, recursively. So that is what we talk about in lecture 8. And right here, we actually trying to apply the evaluation of the tree to our parser. Okay, so right here we actually talk about the whole thing. We have the tokenization. So our compiler or interpreter actually is tokenization, and then actually do parsing build the syntax tree, okay, and then you go into the evaluation stage. Okay, so this one actually is our 3-step, okay, the 3-step that talk about here. We actually already introduced the theory for these 3 steps. So now we are going to look into how we do coding to implement it, okay? So next one is writing production rule. So writing production rule is to write the rule that actually to implement your language. So your language basically is using context-free grammar to describe it, and then you write the production rule and also the action routine associated with it to design your parser. And then later you use a Python language to implement it. Okay, so that actually is what we have. So right here, your expression has the number, and operator is either plus or minus, okay, and a number and a star. Okay, so that's just the rule. And you have expression condition. Okay, condition, you may end and the condition. Okay, end and condition. So right here, this one is expression can be logical expression, okay? And condition can be variable operate number, okay? Can be variable operate number. So these are the production rule for the so-called Boolean expression. So we have Boolean expression, we have integer expression, we have number expression, also Boolean expression, okay? So when they are multiple alternative, the order of the alternative matter, okay? So we evaluate the first one first, right? Because we do recursive descent. We do recursive descent, so basically the first rule you go first, try it, and if it doesn't work, we backtrack, right? But the first rule usually will be taken first, okay? So it has a higher priority, okay? So it has a higher priority. So that's actually is something you need to remember, that actually recursive descent, the rule written first will be tested first, okay? Although in this trivial example, it might seem that order does not matter, but eventually it will, okay? Finally, a production rule only focuses on tokens and other grammar symbols. It ignores the white spaces and comments. So comments and white spaces will be ignored. So the next one, section 11, consideration when building parsers. So previously, we have seen a few simple grammars. However, when trying to parse something more complicated, a number of issues can come up. So we will discuss here, okay? So what are details issues? Previously, we have seen grammar that can handle math expression consists of only addition and subtraction, but you have the precedence, okay, such as time and actually divide. So you may need to have a term. The ideal term is separated from the expression, okay, from the expression. So term including the factor. So this we actually discussed in a previous parser section, okay. So we know that here we have this, okay. So let's take the expression of 3 plus 2 times 5. So actually 3 plus 2 times 5, 2 times 5 will be determined as a term first, okay. So this rule, you should use the term to group up 2 times 5. You should not use an expression for it, okay. So basically you have expression equal term plus term, and 3 is a term. And the second term will be number times number. Okay, it's 2 times number. So you get 3 plus 2 times 5. So these are the rules. So handling the higher precedence in grammar. So when 2 times 5 is passed, the parser immediately return the result of 10. So the result is received by the plus sign turn plus turn step. The addition is performed at the end, yielding the 13 as a result. In summary, you should arrange your rules so that the operators with the lower precedence are at the top, okay, and higher precedence are at the bottom. So basically, what this one suggests is that no matter what grammar rule you do, you should have plus go first. And then you should actually have 2 times right in the bottom, instead of having this one go first. Okay. Okay. So this is the difference between the grammar rule you need to pick up. Okay, pick up this precedence. Earlier, we have mentioned that a recursive descent parser consists of functions that process entity in the text. Now that we know about tokens and production rules, let us redefine this a bit more formally. Each function in the parser extracts a token or implement the logic of a production rule, okay? So here actually is the production. So this one actually, we talk about recursive descent consider function entity, okay? So basically you will match each rule, okay? Okay, so here we have an expression. So expression is you match, evaluate the first number plus evaluate the second number, and there's a read plus sign. And this whole thing will be processed together if you can process this. This one is the evaluation of a expression if it's using the very simple rule, okay? If you're using the very simple rule. So basically, avoid left recursion. This we talked about it already. Okay, left recursion will create infinite loop. Okay, will create infinite loop. So this one you need to avoid the left recursion and also the common prefix problems. Okay. And however, there is a problem with this approach. Okay, you enter an infinite recursion. Okay, that's actually called left recursion. We talked about it already. So also avoid backtracking. Suppose you try to build a parser that parse an operation of 2 plus 4. We wrote a grammar in this way. So you have the expression is addition or subtraction. And addition is number plus number, okay? And subtraction is a number minus a number, okay? So addition of subtraction. This grammar is correct, and it will also behave in the way you expect and produce a correct result. However, this grammar is not what you want to use. To see why this is the case, because we may have the input of 5 minus 2, we will first go for the addition rule and pass the number. Then we will expect a plus sign when we read it, so that will have the backtracking. So we get a minus sign, and that means that we'll backtrack, okay, and you will actually waste time. So basically, if you have a look ahead rule, then the backtracking can be avoided. Okay, so here actually you would like to change the rule like this. Okay, so basically you have number and then use a plus and minus. You actually will pass different rule. So with this one, you have a look ahead bit. Okay, or the so-called follow set. The follow set can have this one or this one. You bring up different rule for the follow set, then you will avoid your backtracking. Okay, so that's the how to construct your rule to avoid that. Okay, so that avoid backtracking. The factoring step is complete. We will avoid backtracking. However, for authentic reason, we will write something like this. Okay, so that one is okay. So section 12, building a base for recursive descent parser in Python. Okay, so we are going to look into how to use Python to do the recursive descent parser. Now that we have discussed the various considerations for parsing, we will build out a calculated and JSON parser. However, before we do that, we will write a base parser class. Okay, has some method for common functions such as recognizing characters and handling errors. This session might seem a little bit long, but it will well worth the patience. Once you complete this session, you will have all the tooling to build complex parsers with very little code required to recognize tokens and implement production rules. So the expression class, okay, so since this is the easiest task by far, so we will tackle this first. So basically, there is a parser error class, okay? So you have position, message, and argument list, okay? So you have position, message, and argument list. So this one is a parser error is a one, it will extend the exception class, and this is a parser error object, and it will show you this one. It actually is your message, okay? And for example, like division by 0 error, and position is your will put your what your message, and you will have the argument that will be put into your message, okay, and your position will be this string. So this is a little bit complicated, that actually your message may be a formatted string, and your argument will put into the formatted string. So this one put into the formatted string, and your position put it to here, and this one put it to here, okay. It's actually this whole thing put it to here. So this one is a parser error. Parser error is to generate the error object, okay, error object. So parser error 13 expect. So this expect actually is what? Is your formatted rule, okay? And 13 is your position, okay? 13 is your position. Your argument is this. So this one you will put into here. That become, okay, expected this, okay, but a bracket position 13. Okay, so the 13 will be put here. That's a position. Okay, argument is here. Okay, and the message original is up to here. Okay, so that is the exception class. So notice that we haven't used a percentage sign with the format string and its argument. Okay. Okay, this is a handle in the string message. String message is converting the error message to string. Okay, we have formatted self.message with the element in the self.position. Okay, now you might ask, why do we want to format it in the string format? Because of this, you can actually replace with a different bracket or parentheses instead of just be able to report the bracket, okay, or curly braces, okay. So it turned out that using the percentage operator to format a string take up quite a bit time. When passing a string, there will be many exceptions raised as the parser try to apply various rules. Hence, we have deferred the string formatting to when it really needed, okay. So this is a parser. Actually, here we have a parser class. So parser class, you have cache that actually is empty, okay? And then you get text. You get text, and then your position starting from -1, okay? And your length, okay, your length of the parser actually is the text -1, okay? So actually the total length is like that. So your RV is your star, okay? Your star. You start function and you serve the end, okay, whether you program end or not, and return your RV. So now that we done the error class, next step is to look at the parser class. So this one is our parser class. So here, okay, this one is a base parser class. Here you will notice that a cache member in the init. We will get back to why it is needed when we discuss the localizing characters. The parser method is very simple. First, it stores the string. Since we haven't scanned in any part of the string yet, we set the position to be -1. Okay, initially it's -1. We haven't scanned any data in yet. Also, we store the maximum index that allow is self.length. Okay, this maximum index always one less than the length of the string. Okay, so basically, that is the maximum length you can have. Okay, self.length, the maximum length to have is a text -1. Okay, and then the pass. Okay, let me see here. We also store. Okay, this one self.length. The assert end is simple. We check if the current position is less than the maximum index. If we reach that, that means that we are done. Okay, we are done. Bear in mind, these methods are inside the class, although we omitted the identification for simplicity. Okay, so here we actually have the base class. Assert end, you actually see if your position actually less than the length. Okay, raise position. Okay, if you end, actually if the position actually less than the length. Okay, the length, you do not move to the length. The passing error. Okay, expect the end of the string, but got something else. Okay, so you still have some text you haven't finished. Okay. Okay, anyway, throughout our parser, we'll look at the character that is one more than current character. Okay, to see why this is the case, we consider that we start with the position -1. We look at the index 0. Once we look at our characters successfully, the self-position will go to 0. And we'll look at the next character as 1, and so on and so forth. Okay, and this is why error use. Okay, the error use the self-position +1. Okay, so here that's why we actually use a self-position +1. That actually we advance to the next character already. So with most language, white space between tokens can be safely discarded. So we can take out that those different one. So therefore, it is logical to include a method that check if the next letter is white space letters, and if so, discard and advance to the next position. Okay, so basically you kind of keep doing, you actually, if this one is in there, you increase it, okay? So basically, where this, okay, you keep advancing until you see something that's not white space letters. Okay, now we have written a function to help us recognize the character in the text. Before we do that, though, we will consider our function from user perspective. So here we will give it a set of characters to match from the text. For example, if you wanted to recognize alphabet or underscore, you might write something like this. Okay, you actually these are actually recognized characters. So there's a character. We will give the char method containing a list of character and range such as A to Z. Okay, so these are the character range. Okay. Okay, the first character has numerically smaller value than the one on the right. Okay, so this one A to Z, lowercase A to Z, and then underscore. Okay, these are considered to be the character range that you will process. Okay, we'll keep the character command, a method containing a list of character and range A to Z. Okay, whatever. Range denoted two characters separated by Z. Okay, so this is the range. Now, if the character at the self text self position plus one matches something in the argument of the self character, we will return it. So if it is one of the legal character, we will return it. Otherwise, we'll raise an exception because it is a illegal character. Internally, we'll process the string into something that is easier to handle. Okay, so we will pass something like this, split range. So here, split character range, you have the characters, okay? You try the cache of the characters, okay? So those characters we put there, okay? If there's a key error, we pass, okay? If that doesn't exist, so your RV actually is empty, okay? Your index equals 0. You actually calculate the length of your characters, okay? While index less than the length, you do the following, okay? So this one is to speak character range, okay? You actually will be, the character actually is your A to Z or A to Z, these are the range, okay? So you have this sense, then your RV actually store range value, okay, range value, okay. So the RV actually eventually will store A to Z, lowercase A to Z, and underscore. These three range value. So three range value means that RV is a set for your the so-called allow symbol, okay. So here, this RV is your allow symbol. You run your star and you put in your allow symbol in there, okay? Those RV are allow symbol. Here, we loop through the character string and look for A minus, okay, followed by any other character. So that actually, you put a certain range into the RV, okay? Then we add the list to RV to the cache, okay? RV, the range of the RV you put into the cache. So you have, okay, your RV actually is the range, okay? And you put your cache of the character. So you put the character, so character is actually, so your cache actually is a dictionary, okay? A dictionary, you have this whole thing, say, your character A to Z, and underline that actually is it actually is a list of the legal sets, okay, ranges. Okay, this one is the character range string, and there is a RV listing associated with put into the cache. Okay, so basically your cache is storing the possible range of the character. It's actually, initially you have the curly brace that actually is a dictionary. Okay, that actually is a dictionary. Okay, so that portion, we actually know that it is to store the dictionary of the RV. Okay. So now extracting character from the text. So we actually fit in some text to from the text. Okay. So here we will characterize. Okay. Extract some character from there. Okay. So self position greater equals to the length. Then we'll raise the error. Okay. So we will get the next character. Okay. We'll get the next character actually from position plus 1. If character is none, then our characters is actually empty, our position plus 1. And when we actually return the next character, okay, we return the character. So character here actually is none. So here you have a character set, okay, and your characters are empty, so you do not have any range, okay. So return the next character. For character range in the split character range, you actually get every range, say A to G, okay, capital A to G. So capital A to G, if the range is 1, that means that it's a single symbol, okay. Then you will create a character and return it, okay. If the character actually has these two range, okay, and then if the character is inside the range, and we will return the character. So basically right here, it actually is what? Whether your character is whether either is in the legal range or is a single character. If so, you will actually, so this function char is to validate every character is in a simple set or not. So that is first focus on the argument characters equal 0. This allows you to call the self.char without giving it to a set of characters. This is useful when you want to simply express a character without restricting it to a specific set. Otherwise, you can call it with a range of characters. So here you can actually put nothing, and then basically you will process it without set. Without set, then you don't validate it. You don't validate it. If you don't put a character set, you don't validate it. It directly return each character every time. Okay, so that's a function that you allow this none to happen. Would help you to do simple testing of character tokenization without validation of the symbol. Okay, this function is very straightforward. First, we will check. We check if we are running out of text. Okay, you can just check if you run out of text. Then we pick the next character and check if the character is none. Okay, in which case we can increment the position and return the character immediately. So that actually is a pass-through mode. Okay, bypass mode. Extracting character from the text. However, if they are a set of character, then you will validate it. Okay, you will validate it as we described. Later on, we'll see how this function recognizes tokens. Okay, so you will validate whether your data is in the range or not. Okay. So apart from extracting each individual character, recognizing keyword is a common task. So now you have some keywords. So keyword need to be checked first. Okay. So keyword need to be checked first before you go into what? Keyword need to be checked first. So for example, that for loop, you check this one first before you go into check the I variable or text variable. This one actually is by the tokenization. You need to validate easy simple. But if you hit the keyword, you should process it first. Okay, you should process if there are some keyword first. So okay, so we use the keyword to loosely refer to any contiguous string that has its own entity, okay, and we may have white space before or after it. So say for loop, okay, you have white space before and after it, okay. But sometimes you may have this one, and as we say, you can add extra space before and after it. That would actually help to help the tokenization, okay. Okay, this is the code for recognizing the keyword. So basically, you have keyword. Keyword is actually a list. Okay, so self that eat white spaces. So this one will add white spaces. Okay. So basically, if the keyword in keywords, each keyword in keywords your low, okay, and your high, you calculate. So you try to check the text in this location is a keyword. Then our position will advance by the length of the keyword, okay? And then we will eat some white spaces and we will return keyword. So keyword would get tokenized using this portion, okay? Keyword will get tokenized using this portion. If you actually have error, okay, then actually, if actually there's an error, then you will raise the exception. Okay? You raise the exception. Okay, I think right here actually, right here is the right here the whole thing. This one actually this one here. Okay, this whole thing. I think it actually need to be adjusted for alignment. Okay, it need to be adjusted for alignment. So this one actually should be you actually should be like this. Okay, you have if this one greater than that, you actually need to be aligned. This one, if this one you have the token, you get it. Okay, this one you should get it. Okay, it's actually get it. Okay. So here, this one, I'm not sure for this portion. Okay, so this one that's actually just put it for the time being. We will check later. Okay. Let me compare my text code. Okay, let me compare my text code. So right here, this one may have some trouble. Okay. So let's see this one that we do have the code over here. Okay. So let's look at this one, calculator. So there's a char here. We have the char function pass error. Okay, here is a keyword. Okay. So keyword, this one with race. Okay, this one need to be inside. Okay. So this one, the race error actually is on the same level as 4. So that one, actually the second one is on the same level as the 4. Okay, so sorry, it actually should be, this one we should actually return it to the 4 level. So here you check it, okay, you check it and then you return it, okay. So right here, if actually you do not find, so basically you find all the keyword, if do not find any do not find any keyword, okay? You do find any keyword that match, okay? That match, and actually your position also out of space, okay? Out of space means that your keyword is used in the wrong way. You will raise the error, okay? This one you raise it. So this one you need a tag, but this one you doesn't, okay? This one actually is that you actually advance your keyword. So for example, that you have something like 4, okay? But it doesn't follow by a space, but it follow by a certain wrong word, and you match the keyword in the wrong way, then you may raise the error. So if the keyword doesn't position right, you will report that there's an error. Okay, you will report there's an error. So this one, let me save. Okay, let me save it. So we are on the basic parsing class. Okay, we are on the basic parsing class, and we actually finish this one. Okay, next one. Okay, extracting keyword and symbols. This method take the keywords such as self keyword is a different keyword. So you have this different keyword. Method strip the white spaces and check if we run out of the text to pass. If we have a keyword and we run out of keyword to pass, then you will fall into this error part. Okay. And if we run out of space to card, then you iterate through each keyword and check if the keyword exists in the text. If does not find anything, we'll strip the white space and following the keyword and then return the keyword. Okay. If it doesn't run out of the space, but if it run out of space, it means that the keyword is put into the wrong location. However, it doesn't find anything and it checks the group and raise pass error, stay in the keyword doesn't exist. So you kind of try. You need to have a keyword somewhere, but your keyword is not found. Then you will actually return error. Okay, so this one actually keyword is a matching function. Okay, matching function in your parser. Okay, that's a matching function. So keyword. So this is keyword. This char is a validation for character. Keyword is a validation for the so-called keywords. And if we look at the previous lecture, our lecture 12, lecture 12, okay. Lecture 12, we do talk about the so-called recursive descent for the terminal. So basically, each rule, your terminal, you will evaluate terminal function. So that keyword and the char is the procedure we talk about here. Each of the terms related function. Okay, each of the terms related function. Okay, each of the terms related function. Each of the terms related function. Okay. Now let's go back to lab portion. Okay, let's go back to lab portion. So we are okay. We actually sorry. We are actually right here. Okay, we finish this one. That's a keyword function. So you track and check the keyword. Okay. Now this one is matching multiple production. So we have item. Item can generate number or word. Okay, so this one is two different production rule. Okay, so remember these are two different production rule. So we check item. So item will check item and it white space. Okay, and then try self the number. Okay, so that's the first rule. If there is a passing error, we will backtrack and we'll try self that word. Okay, and you will pass using self the number or self the word. So this one is your or. Okay, so passing error. So actually we will eat the white space. So eventually we will return the so-called RV. Okay, RV will be returned. RV is a return value. Return value is your return value after you evaluate the item. Okay, so item is a function. You will do that. Okay. So here you are matching certain rule. Okay, so you have the rule. You try to match the rule with some tokens. Okay, so you pick up every rule. Okay, you pick up your initial position. You took up every rule, so you actually get attribute of the rule, okay, and then it white space. You try this one. Get attribute means that you are going to apply the rule, okay, and then you will get exception, okay. You get exception if you actually have exception, have some error, so the rule cannot be applied to it. So you apply different rule. If the rule fail, you actually will go to the pass error. Okay, you go to the pass error and cell position will, this one will do the backtracking. Okay, do backtracking and try different rule and then backtracking, by different rule and backtracking. Okay, if the last rule error is equals 1, then that means that no rule can be applied. You erase the error. So here you have a set of the rule. Every time you try one rule and then see if the rule can be applied. If it cannot be applied, we do backtracking, and then we try second rule. Second rule doesn't pass, you continue until all rule that doesn't pass, you actually will erase the error. If there is a certain rule that pass, you will return the return value. Okay, so this one is applying certain rule to your tokens. Okay. So here, this one is to self the match number and the word. So number and word, these are the two rules you apply to, number rule and word rule. Okay. Number rule and word rule will be applied to. So this one is a list of the rule will be passed to there. Okay. The list of the rule will be passed there. Okay. So how does this work? Match take a method to method name to run. Okay. So basically you get a method name to run. So you actually will apply the rule. Rule is a name. So this one basically you get the name. So that name is a word. You run the function called word. So you actually tokenize the word and evaluate. Okay. So this one, remember, this get attribute is a what? Annotated. Actually, the declarator. Okay. The declarator, we talk about it in chapter 8, lecture 8. In lecture 8, we do talk about the attribute. Okay. The attribute. So this one is actually you kind of use that get attribute, and the attribute rule will be used as a function, and you will run that function. Okay, so the rule can be passed over here. So this one give you the function, the rule, actually the so-called example of applying the string as the name of the function, and you can evaluate different rule. Okay, so you apply this. Okay, so this one is to apply the function and name. So then it iterate to all methods of name, fetch each method using its name via get attribute. So get attribute will get attribute from self. Okay, you actually from self, and then actually the rule, you will actually apply the rule to it, and you will get that. Okay, you will get that. Okay. Okay, so that actually is the duo you get over here. This duo is the variable in this current object. Okay, current object, you pass a self to it. So your current object is the self. Okay, the self. You actually apply it to it. Okay, apply it to it. So you get a function using the string as a name of a function. Okay, so something that you can call a function. However, there is an error, then it reset the position. So this one is a backtracking portion. You reset the position to the value that was there before trying to match a rule. Then it tried to select good error message by using the following rule. When matching multiple rules, many of them might generate an error. The error was generated after passing most of the text. Is probably the error message was we want. Okay. To see why this is the case, consider that ABC1, try to call the number, it failed at position 0, okay? Try to use the word, okay, it failed at position 2, okay? Looking at the string, it's quite likely that the user wanted to enter a word but made a typo, okay? If two or more error rule end up in type, we prefer to tell the user about the rule, all the rule that it failed. So basically, here actually it will join all the rules together, okay, and reporting all of the errors. At this point, we have all necessary scenes for in our parser, and all values is sure exception. However, sometimes we want to only match a character, keyword, or a rule. If it's there, okay, without inconvenience of handling exception. We introduce 3 small helpers to do just that. Okay, in case of an exception, we look when looking for stop. These will return none. Okay, so here this one maybe character, maybe match, maybe keyword. Okay, so here we will return maybe character, will return a char with the character. Okay, char with it. So we actually return char with letter. So this one you have a char with letter, you will return you the so-called RV return value by the characters. Okay, so here this one actually, if you maybe match, so you apply the match of the rules. Okay, if it has an error, you return none. So here you may apply maybe character, you try character, and it fail, you will return none. Okay, you try keyword, if keyword fail, you return none. Okay, so that one would allow you to bypass the error, and then you actually would be able to try keyword, try later, try key matching rule. If the error, you return none. Return none means that you do not successfully evaluate with that try. Okay. So operator may be plus minus, okay. If your operator is plus, okay, you add two numbers, it's minus, okay, maybe keyword plus and minus. If operator actually, that would be the return. If it's successfully, okay, you will use a plus, okay. So you actually perform the operation, okay. If none, and then you will do something else. Okay, so let's look at simple example of calculator. So now that we have already built the foundation of writing the parser, we will build our first parser. We are able to parse mathematical expression, addition and subtraction, multiplication and division, also parentheses. Okay, we will begin by visualizing the grammar in the form of production rule. So here we have expression produce, turn, okay, plus or minus turn, okay, this one expression. So each turn will be number time divide number. So here, these are the symbol we want to have, okay. So, and then our expression, okay, so that's a production rule. So our expression would produce actually plus minus turn, okay, and turn can be factor, multiply or divide factor, and factor can be expression with parentheses or number. So these are actually recurring, including the nested code. This one doesn't include the nested code, okay? And this one include the nested code, okay? Okay, so here we have a calculator parser, okay? Calculator parser, we actually will star function will return the evaluation by expression. So expression is top level evaluation function. Your text will be evaluated by expression first. Okay, so the top level tree that actually is your recursive descent method. The top node is expression. Okay, expression. So that's our calculator. So our calculator implementation top level is expression. So expression will match the turn. Okay, match your turn. Expression will follow the rule here we define. Is a turn and then this. Okay, it must be in this. Okay, so that's the first one we would check is the turn. So turn will match turn. If true, okay, we actually may continue or may not continue. Okay, so that actually is turn plus turn plus turn plus turn. But you may only have one turn. Okay, you may only have one turn. So you will match the turn. And while true, okay, you would try keyword. Next one followed by a keyword. We will do keyword and then turn. Okay, turn and match keyword and then turn. Okay, if the operator is none, we actually break. Okay, we finish that. We finish that, and we'll return the value evaluation for the turn. Okay. Okay. Okay, so here, if you finish the evaluation turn, your RV that evaluate by this, say you have 5 plus 2 plus 3. So this 5 is the first RV you have, plus 2 will have the turn will be plus into your RV. Okay, 3 will be plus into your RV again. Okay, so that's the rule for this expression rule. Okay, and this one is to evaluate your rule for this expression. This one is the rule implementation of this guy. Okay, that's the implementation of that guy. So that's one is the expression. Then we will actually look into the turn. The turn is a factor multiply or divide by factors. So this one, the same thing. This one is to match your rule for the middle one. Okay, for the middle one, that's a third with this, the middle one. Okay, the last one we look at the factor. The last one we look at the factor. This one is expression, and then last one we look at the factor. Factor actually may be a parenthesis followed by expression, followed by a keyword or parenthesis. Okay, and then if you match, you will return the return value. Otherwise, you will return the match result for number. Okay, you may return it. So if it's not, so this one actually is implementation of the last rule. You have factor equals this. Okay, so here apparently you see that this one give us a very good discussion of how to implement a simple expression evaluation in the recursive descent. Okay, here we have a number. A number is checking for text. Okay, so there's a sign plus or minus. Okay, maybe keyword. So here you will actually determine the sign. Okay, determine the sign. If sign is not none, we will append that to your character set. Okay, your character set. Okay, and then your character set append this. Okay, you continue to chart this. Okay, so you actually, this one is to, this portion is actually do what, doing your d plus. Okay, d plus one or more character. Okay, one or more character. So this is the integer. Okay, and maybe followed by a decimal point. Okay, and then you have another way to do this one is a fractional part. Okay, fractional part. This portion is a fractional part. And eventually you join the whole thing together, and then you actually evaluate by the flow. So before you evaluate that, you actually already have a sign plus or minus here. And this whole string joined together, you will be actually evaluate your return value. Okay. So right here, if any of them is not 0 to 9, then you will not evaluate. Okay. So here, actually, you will keep evaluating it. Okay. So until you actually evaluate the character already none. Okay. The character already none. You actually do not get a character, then the tokenization for the number is finished. Okay, so this one can actually what, tokenize a number or a integer or a floating point number. Okay, although the function is long, it's fairly simple. We have the character list in which you put into the character of the number. Okay, we look at the plus minus sign. Okay, and then that's the first one we add into our character list. Okay, then we look into the so-called integer part, and then decimal point, and then the fractional part. Okay, and then we convert it to a floating point number. So if it is a main program, we will create calculator parser to a parser. Okay, so this one is top level. Top level, we will have the replete format. So you actually pass the input greater equals. Okay, so that's your initial portion, and you will keep typing in. Okay, if the keyboard interrupt, you print. Okay, otherwise you will actually keep passing with the input you have. You echo this one, and you enter a string, and the string will get parsed. Okay, the string will get parsed, and okay, now we have the first gradient recursive descent process. So this one, let's actually look at the example. So here we are in the calculator gradient recursive descent portion. Okay, so right here, that's actually we need to bring up our break window. So here we have this recursive descent process. So let's bring up the code, Visual Studio Code. Okay. So here, before we run it, okay, let's actually look at the overall code one more time, okay? Let's look at overall code one more time. So right here, actually, you have parser exception. Okay, so this one parser is the exception generating of the exception that we talk about it. And then we have parser class. You have the cache. Okay, cache is used to put in the temporary return value. Okay, the dual or something. Okay, then you actually call the star function. The star function will start from the so-called expression. Okay, the star function actually will is a star function you will call. It actually this one it actually extend the parser. The parser we define the star function. So this one actually the star function over here. Okay, the star function over here. Okay, you run self.star. Okay. You run self.star, but basically the star function is to evaluate the expression, okay? And you will assert that after the evaluation, you already consume all the character, okay? And the return value of the evaluation of that expression will be returned. So starting from here, we go recursive descent to the lower portion. So here, each white space split character range that we talk about different function. Evaluation of characters, okay, and keyword expression, match the rules, and then maybe character, maybe match, maybe keyword. And this one, you actually start to evaluate expression, term, and factor, and number, okay, and then the main function. So we actually go through every single line in our slices already, okay. So this one, let's actually do Python. Okay, this one called the program name of this guy is called cal_parser. So calculator parser.py. Okay, so we got a greater sign. So here that's evaluate 3 plus 3. Okay, so that's evaluate 3 plus 4 times 2. Okay, that's evaluate 2.456546 plus 3.2222. Let's try something error. Okay, so 2222 it actually error. Okay, let's try 444 plus 2. Okay, error. 4 plus 2. Okay, 2 plus 2. Okay, some more spaces times 4. Okay, it is correct. Okay, so the white spaces will eat out the white space over there. Okay, so that has more spaces, and then 10 plus 2. Okay, it actually still work. Getting now, that's actually do more return. It actually will do this. So let's do Control D. Okay, Control D will actually get out of the program. Okay, so this one is our calculator parser. Okay, our calculator parser. So now let's actually next one that actually continue our parser portion. Okay, continue our parser portion. Let me close this one. Continue our parser portion. The next one is the JSON parser. Okay. So next one we have the JSON parser. So JSON parser will pass the JSON data type. Okay. Okay, so first you need to know about what is JSON parser, okay? So JSON is a data interchange format that supports basic data structures such as a number, string, list, and also objects, okay, for JavaScript, okay? So since Python already have JSON module, we are going to aim at a little higher and build a JSON parser that support comments, okay? You can also comment trading commas and actually encoded string as well. Okay, implement this parser will teach you how to handle comments. It will also illustrate how making a easy to use language can make parsing complicated, okay, and how you can deal with such a situation. So here we may have a JSON with sharp comments, okay, sharp comments. So here your data field is size 1.5x, okay. You're seeing actually with a dictionary, okay, an object, okay, an object in JavaScript, okay. And JavaScript's object is actually Python's dictionary, okay. And then you have key list or key and value pair, key and value pair. So this is actually a JSON, but this JSON actually use the sharp sign as the comment. So that's actually supported. Okay, and trading comma and unquoted string and trading comma will be allowed. Okay, it will go through the next line. Okay, so our extended JSON stick to the same data type that JSON support. JSON have four basic data type: null, boolean, number, and string, and two complicated data type. Okay, list and dictionary. Okay, or object. You should call it object. Okay, list and hashes look similar to the way we do in Python. Okay, in Python dictionary. So here actually we have star actually will produce any type will produce primitive type that's actually single data or a complex type. Complex type can be list or map. A primitive type will be null, boolean, and number and string. These are the basic rules. Okay. So this grammar is fine for passing a regular JSON, but need a little bit tweaking in our case since we are going to support unquoted string. Okay, so unquoted string that actually is this is without a quote. Okay, it's a number, but unquoted string. Okay, it is a string without quote. Okay, we write unquoted string. This means that first we would have to get full set of unquoted characters. Next, we will analyze the character and determine it is a number or is it a string. So we need to determine the unquoted string is a number or unquoted string is a string. Okay, so we will combine the number and unquoted string into a single category called unquoted, and then unquoted we separate it into quoted string and basically number and actually also string. Okay, so basically primitive data type we have null, boolean, okay, and quoted string and unquoted string. Okay, and unquoted string can be a number or can be a quoted string. Okay, so in addition, we know order of the rule is important, so we should do this way. Okay, so let's continue. We have a JSON parser. Okay, we have class JSON parser. And then we have each white space. Okay, each white space I think is similar. Okay, it's similar. So we actually, and then next one is implement the parser dealing with comment. Here we'll keep track of whether we are processing a white space or a comment. Okay, so you treat the white spaces and comment in the same way. We basically just eat the white space. Now you eat the comments. Eat a comment, anything with a sharp, we will eat that. Okay, so basically we start and we have the any type and primitive type. Okay, so this is another rule that we talk about so far. That's a rule we talk about so far. So this rule we implemented. These are very straightforward now. Okay, and then we have the passing. So we actually implement the passing for the list. So the return value equal empty, and we start with the this and ending with this. So this one we are going to actually implement the so-called ID, comma, ID, comma, ID, comma, ID things. Okay, so any type. Okay, matching any type, and then actually we will eat a comma. Okay, and then if not this, we actually will break. If at the end we do not see a comma, then we will break. Okay, we will finish. So this one basically it is using this. Okay, and then this format. Okay, it is using this kind of format. Okay, we begin by reading of the initial square bracket, okay, and you follow by the matching of any type, okay, and that many type is the first value, okay, and then it's a comma with the any type, comma with immediate, I don't know, and at the very end you should match with a bracket again, okay. So map, okay, next one we have map and pair, okay, map, actually you start with this one, okay, and you match the pair, okay. Match the pair means that you have the so-called A comma B, okay, that actually your key and value, okay, your key and value. So we will actually create a dictionary of these, okay. Item 0 and item 1, okay. You assign this, create a dictionary item into the dictionary, okay. Maybe you created that. So you doing that pair, you have a pair, you actually have matched the uncoded string, coded string or uncoded, okay. So coded string, you actually try to pair, okay. So pair, you have a comma, okay. So you match that for the key. Key can be coded string or uncoded string, okay. So this one is used. This one is to evaluate your pair. This one is actually mention this pair. So this pair is actually mention this rule, okay. Mention this rule. So this apparently you can see that this whole infrastructure is very solid. You write a similar function, you can create the parser for different languages, okay. And then you have quoted string or not, okay. And then you try to see the type of the key is actually not string, okay. If it's not string, and we actually will raise error. It must be a string, okay. Must be, no matter it's coded or uncoded. Uncoded will return a string, okay. And then it's actually followed by a column, and then any type of data at the end. Anytime we already explained it, and then you return key, comma, value, two value out of your pair. That two value you actually will be passed over here. That will be your item 0 and item 1. Item 0 and item 1 will be put into your RV as a dictionary, okay. So that actually is creating map and also pair. So the null, you actually check if the keyword null, okay, otherwise return null. This one is like the maybe, okay, the maybe portion. And the Boolean, you have the keyword of the true or false. So you need to use the keyword now, okay. Recognizing uncoded string and the number, okay. So here we will look into recognizing so this one determine the uncoded, whether it's a string or number, okay. So if you import string, okay, import string, this one actually the possible string characters. Okay, let's come to here. So your acceptable character are these, okay, these, okay. So you do have some range. You do have some range, okay. So uncoded means that you will actually check this. It can be number, it can be this whole thing, okay. So now let's look at it. Okay, so here we actually character acceptable list. So we create range and put it into characters. So this one, the characters now is a range of a single symbol. Okay, so that's the characters. So maybe character acceptable characters. Okay, okay, and actually is actually char. Okay, you actually try to do that. You actually try to check if the maybe character it actually we actually while true, while you actually why is it true, okay, why is true, you do this. So this one, let me adjust it, okay, adjust it. So basically while true, you actually, this one should be dropped to here, okay. This one should be dropped to here. So basically every time you actually try to tokenize a character, okay, if it's not none, if it's none, you break. That means that the end of the uncoded, okay. If a character is in these, okay, then it is number type maybe floating, okay, maybe floating type, okay. if you see the natural scientific notation, okay, if you see the scientific notation, if you see the scientific notation, it actually maybe 4, okay, we would then we append a character into the chars, okay, the char actually is, you try to create a first one integer, okay. If it's an integer, we actually number type integer, okay. Okay, so here we do that. So at the end, we join the chart together and we will do evaluation, okay. So here unquoted actually you will determine it, maybe it's integer, maybe it's float, okay. Maybe it's integer, maybe it's float. So actually join together, if we evaluate whether it's a number type or not. If number type is actually is not a number type, if it is not a number type, then we will return the RV. RV is the join of together. So RV case, you will create string. So this one join, and then using the try error part, this portion will you actually determine whether it's a number type or it actually a string type. Okay, so you evaluate whether it's a number type first. If the number type is wrong, then we determine it will be an unquoted string. So this case is unquoted string. This case is actually a number. Okay, so unquoted string will actually make it a string and return. Okay, so unquoted will return either a number, or it actually will return a string. Okay, so right here you initially try to set the type to be integer. Okay, try to set the type to integer, and then you kind of create a character. Okay, try to create a possible character. Chars actually is the set. Okay, the different ranges. Okay. Okay, so actually regarding this one, okay, this one actually we have a quoted string. Quoted string is determined that you are a quoted string, so you actually may have a quote, single quote, okay, and then that's a starting, and the you may in the middle you may see the escape sequence like this, okay. So there are many escape sequence, and your char is your character. So you actually try to evaluate a char character. If the character is actually equal quote, okay, equal quote, so that actually you finish it already. If not equal quote, okay, it is actually slash slash, that actually is backslash, okay, 2 backslash, okay, it actually is we try to see if it actually is a step sequence or not, okay. 2 slash means 1 slash, so you see 1 slash, you see if it's in the escape sequence or not, okay. So if the escape actually is U, okay, U, then actually you try to find out the Unicode, okay, that actually is a Unicode, okay. Okay, otherwise you will actually use the exceptions to get another sequence to find out which letter it is. Otherwise, you append the char to the characters, and then you will have all of the character in the list format, okay? And then that you join together to a string, okay? Join together to a string, so that eventually you actually import, okay, pp print. Okay, this one actually has minor issue here. This one, so this one is from pp print. Okay, you import your pp print. Okay, after that you do this. Okay, sorry for that. This one actually a little bit messy. Let me actually adjust the font size. Okay. Okay, so this one actually is you main function, you actually import your sys or you import pp print, pretty print. Okay, so same thing. This one will go to run your parser, and then actually you will pass it. Okay, pass it, and then go into the repeat format. Okay, going to the view. So let's actually look at it now. So right here, let's actually change the folder. So here we do go into this folder. That's a JSON format parser. Okay. So right here, same thing. The error is there. Okay, string there. Parser. Your parser is the same parser class. Okay, the same parser class. The basic rule are the same. And JSON, you will actually redefine the it white space with the comments. Okay, with the comment eating the comment. The star you match with any type. Now your star symbol is any type. So basically, when you use it, you can always use the parser as your base. Then you add your extra language rules into your custom class. Okay, so right here we redefine the evaluation function of your JSON language, like including any type, primitive type, complex type, list type, and the map type, and pair type. Null. Okay, this one we already talk about it one by one. Okay, so this one actually okay. So now let's look at it. Okay, so here let me go to here. Okay, so let me actually do change directory. Okay. So let's do Python, okay? And the program name right here is called JSON underline parser, okay? So JSON underline parser. Okay, let's run this one, okay? So right here, it doesn't have the echo, okay? It doesn't have the echo. So let's get started with 1, 2, 3. Okay, let's see. Here, actually, you pass from keyboard, okay? And actually, you print error. You pass error, you actually get the error, okay? You pass it. You have a pretty print. So here you run the parser, okay? JSON parser, and you pretty print it, okay? You pretty print it. So from your standard input, okay? So there is no no sign. You actually, so right here, that's actually ended. Okay, ended, you actually will get the echo of this. Okay, so let's try this one. We have the Python JSON underline parser. Okay, now this time I'm going to try more difficult one. So let's add a object. Okay, so A1 comma B comma, okay, 2 comma, okay, C colon and space 10. We close in with curly brace. We are finished. So that will create my dictionary. Okay, that one more time. That's the Python, okay, JSON underline parser, the py. Okay, this one let me have some spaces. And then I have a this, okay, and A actually 1, 2, okay, 3, 4, okay, this one actually is a dictionary. And then I have actually 1, 2, 3, okay, this, Control Z. So this one we have an error. We have an error because we are expecting a bracket in a 13. So basically this one, the problem right here is that you cannot use the number as the key field. So let's try it one more time, okay? You cannot use the number as the key field. So let's actually do Python, okay? JSON underline parser, Okay, so this one does have this one, break it. Okay, here actually you may have A1, B2, this one, 3, 3, 3. Control it by the way. This one you go into some problem. Okay, let's actually use control D one more time. So actually, it actually have a control D. This control D is not allowed. So they don't accept this. Okay, they don't accept this. Let's try one more time. Python, JSON. Okay, parser. Py. Okay, that has bracket. Okay, let's try this one more time. Okay, just do this. Okay, and control G now. So this one you have this one is wrong. Okay, this one is wrong. Python JSON parser the py. Okay, I'm sorry. Python JSON underline parser the py. One more time. Okay, so we have this one. Curly brace A and 1, comma B 2 and curly brace and bracket. So here we do control G. Okay. So this one is successful. So be careful. This one, I tried several versions, right? So if you try to control G at the same label, it will be wrong. Okay, it will be wrong. And if you do the next line, it actually is okay when you finish your typing. Okay, so you can play around this one, and it's very interesting. Okay, so that's that. Let's actually have one more. Okay, one more. So here, let's look at section 15, okay? So we finished two basic and simple parser. So if we want to build other kind of parser, so basically now we are able to work on other parser, okay? So white space sensitive languages, okay? Before we begin, some languages are white space sensitive, okay? And you cannot eat the white spaces. So in those one, you have to actually consider to use different rule, okay? An example of such language is that A equals 10 is different from A space equals 10, okay? With space and some other shell, A equals 10, set environment variable, whereas A equals 10, run a program A with equal and 10 and combine arguments, okay? So that can be different. So some language actually is different, okay? So those one is actually case sensitive. So in that case, you need to design your rule for command and keyword and argument list in a more clear way, okay? In a more clear way. So white space based indentation. So some language like C or JavaScript using the curly braces to indicate the body. Okay, so some languages such as Python that would need the indentation. So indentation by itself is some sort of grammar. Okay, in Python language, so you may need that indentation rule. Okay. And okay, this portion I just want to mention about this. Okay, when you design some language, these are something you need to study. Okay, we do not provide the code for this. So okay, so here we finish the chapter 9. Okay, in this chapter 9, the lecture 12 we cover the basic theory for the parser, the first part of the parser generating of your syntax tree. The 9B, lecture 13, we focus on the evaluation of the syntax tree. And the second half of 9B, we use the recursive descent to design a simple version of the parser. And it is working for the JavaScript language and also for the calculator language. Okay, thank you. Bye now.